In a basement laboratory at Harvard University, a woman in a lab coat watched a beam of light come to a complete stop. Not slow down, not flicker, stop. For a fraction of a second, inside a cloud of atoms colder than deep space, light itself stood still, trapped, frozen, held captive by human hands. If you had told Albert Einstein this was possible, he would have told you that you had broken one of the most sacred rules in the universe. And yet it happened. It was measured, it was published, and almost nobody outside of physics knows the full story of how it was done or why it matters more today than it did the day it happened. This is the case file on the day light stopped moving. For over a century, one number has anchored nearly everything we understand about reality. 299,792,458 meters per second. The speed of light in a vacuum. Not a suggestion, not an approximation. A constant so fundamental that Einstein built the entire architecture of special relativity on top of it. Time, space, mass, energy, all of it bends around this one unshakable number. Nothing with mass can reach it, nothing can exceed it. It is, as far as physics is concerned, the speed limit of existence itself. So when word started spreading in the science world that a physicist had slowed light down to 17 meters per second, slower than a person riding a bicycle, and then 2 years later brought it to a dead stop, their reaction wasn't excitement, it was disbelief. Because on the surface, this sounds like a violation of one of nature's most protected laws. It sounds like science fiction dressed up as a press release. It sounds, frankly, too strange to be true. But here's the twist this case file exists to resolve. Nothing about this broke Einstein's law, not one particle of it. What happened in that lab was not a loophole in physics. It was one of the most elegant demonstrations of physics ever engineered by human hands. And understanding how scientists tricked light into slowing down and then stopping altogether will change the way you think about light, matter, and the universe you're sitting in right now. Let's build the case properly, from the ground up, the way any real investigation should. To understand how something as fast as light can be stopped, you first have to understand what the speed of light actually refers to. Most people assume it's a single, unbreakable rule that applies everywhere, all the time, no exceptions. That's only half true. The number 299,792,458 meters per second is the speed of light specifically in a vacuum, empty space with nothing in the way. The moment light enters a medium, glass, water, air, diamond, it slows down. This isn't controversial. It isn't fringe science. It's something you can observe with basic equipment in a high school classroom. Think about a straw sitting in a glass of water. It looks bent at the surface, doesn't it? That visual trick, called refraction, happens because light moves slower through water than it does through air. The light entering the water is forced to change its angle because it's now traveling at a different speed. Diamonds sparkle for the same underlying reason. Light slows dramatically as it passes through the dense crystal lattice, bending and bouncing in ways that scatter color in every direction. Even the light coming through your window right now is moving slightly slower than it was a nanosecond earlier in open space, because glass is denser than air. So slowing light down is not new. It's not even rare. It happens billions of times a second, all around you, all the time. But there's a massive difference between shaving a fraction of a percent of light speed by passing it through glass and taking light from 670 million miles per hour down to 38 miles per hour, a speed slower than most cars on a residential street. That's not a fraction of a percent. That's a reduction by a factor of roughly 20 million. Glass slows light down by less than half. Diamond, one of the densest naturally occurring materials on Earth, only manages to cut light speed by a bit more than half. Nothing in the natural everyday world comes remotely close to a 20 million-fold reduction. To achieve something on that scale, you can't just find a denser material and shine a laser through it. You need to build a medium that doesn't exist naturally anywhere in the universe, one engineered, atom by atom, under conditions colder than the space between galaxies. To understand how anyone pulled that off, we have to go back to a laboratory in the late 1990s and a physicist named Lene Hau. Lene Hau was a Danish physicist working at Harvard, and she had spent years chasing an idea that most of her peers considered borderline impossible: creating conditions so extreme, so precisely controlled, that light itself would be forced to behave in ways nobody had ever directly observed. Her tool of choice was something called a Bose-Einstein condensate, a state of matter so strange that it barely resembles anything in your everyday experience. Hau's path to that laboratory was not a straight line. Growing up in Denmark, she was drawn to mathematics long before she found her way into physics, and by her own account it was quantum mechanics, the branch of physics that governs the bizarre behavior of particles at the smallest scales, that eventually pulled her in completely. She trained at Aarhus University, spent time at CERN, the massive particle physics laboratory in Switzerland, and eventually landed at Harvard, where she would spend the rest of her career pushing the boundaries of what quantum optics could actually demonstrate in a controlled laboratory setting, rather than just describe on paper. By the time she began the Slow Light project in earnest, she had already spent years building the underlying tools and techniques that would make the eventual result possible. This wasn't a lucky accident stumbled into overnight. It was the product of a specific, deliberate research trajectory, years in the making. Here's the plain version of what a Bose-Einstein condensate actually is. Take a cloud of atoms, in Hau's case sodium atoms, and cool them down to a temperature just a few billionths of a degree above absolute zero. Absolute zero is the theoretical coldest temperature possible in the universe, the point where atomic motion essentially stops. Nobody can actually reach absolute zero, but Hau's team got astonishingly close, using a combination of lasers and magnetic traps to strip away almost every trace of thermal energy from the sodium atoms. At that extreme cold, something remarkable happens. The individual atoms stop behaving like separate, distinct particles bouncing around independently. Instead, they collapse into a single collective quantum state, acting, in effect, like one giant superatom. This is the Bose-Einstein condensate, first predicted theoretically by Albert Einstein and Indian physicist Sachendra Nath Bose back in the 1920s, and not experimentally created until 1995, just a few years before Hau's experiment. It is one of the strangest, most exotic states of matter that exists, and in the mid-1990s only a tiny handful of labs on Earth had the technology to create one at all. It's worth appreciating just how long the gap was between prediction and proof. Bose and Einstein worked out the theoretical mathematics describing this state of matter roughly 70 years before anyone actually managed to create one in a laboratory. For decades, the Bose-Einstein condensate existed only on paper, a mathematical curiosity that most physicists assumed would remain forever out of experimental reach, because achieving the required temperatures seemed technologically impossible with the tools available at the time. It took the development of laser cooling and magnetic trapping techniques in the 1980s and early 1990s, technologies that earned their own Nobel Prizes, before physicists finally had the tools needed to chase temperatures low enough to make Einstein and Bose's prediction real. When the first Bose-Einstein condensate was finally created in 1995 by a team using rubidium atoms, it was considered such a landmark achievement that it earned a Nobel Prize in Physics within a matter of years. Hau's team was building on that breakthrough almost immediately, adapting the underlying technique to sodium atoms and pushing it toward an entirely new application. Not just creating this exotic state of matter, but using it as a tool to manipulate light itself. Hau's team built their own version of this technology from scratch. The process began with something almost comically low-tech compared to what came after. A device they nicknamed the candlestick, which literally wicked molten sodium metal the way a candle wick draws up wax, releasing a controlled stream of sodium atoms into a vacuum chamber. From there, a battery of finely tuned lasers cooled those atoms down, stripping away their kinetic energy step by step, while magnetic fields corralled them into place. The result, after enormous engineering effort, was a cloud of sodium atoms sitting at a temperature of less than half a millionth of a degree above absolute zero, one of the coldest objects that had ever existed anywhere in the observable universe, colder by far than the depths of interstellar space. Now here is where the actual light-slowing trick comes in, and it's worth slowing down, pun very much intended, because this is the part most casual retellings of this story skip entirely. Under normal circumstances, sodium atoms are almost completely opaque to the specific frequency of laser light Hau's team wanted to send through them. If you fired that laser at a normal cloud of sodium atoms, the light would simply be absorbed and scattered, the same way a beam of light gets swallowed by a thick fog. But Hau's team used a technique called electromagnetically induced transparency, a genuinely brilliant piece of quantum engineering that essentially unlocks a normally opaque medium and makes it transparent to a specific beam of light, but only under very precise conditions. Here's the mechanism, in plain terms. The team first fired a coupling laser into the ultra-cold sodium cloud. This coupling laser altered the internal quantum states of the sodium atoms in a very specific way, creating what physicists call a quantum interference effect. In simple language, it opened up a narrow window of transparency inside a medium that would otherwise completely block the incoming light. Then, through that narrow window, the team fired their actual signal laser, the pulse of light they wanted to slow down. Because this transparency window is so narrow and so sensitive, the refractive index of the sodium cloud, essentially how strongly the medium bends and drags on light passing through it, becomes extraordinarily steep. And that steepness is the entire secret. The group velocity of the light pulse, which is the speed at which the overall pulse of light actually travels through the medium, becomes tied directly to how sharply that refractive index changes. In a normal material like glass or water, that change is gentle, so light only slows down slightly. But inside Hau's engineered condensate, the change was almost vertical, an enormous sudden shift concentrated into an incredibly narrow range. That extreme steepness dragged the group velocity of the light pulse down to a crawl. When Hau's team ran the experiment and measured the results, the numbers were almost unbelievable. The light pulse, which should have shot straight through the cloud at hundreds of millions of meters per second, emerged on the other side traveling at just 17 meters per second, roughly 38 miles per hour. Slower than highway traffic. Slower than a decent cyclist on a flat road. Light, the fastest thing in the entire universe, the cosmic speed limit itself, was measured moving slower than a golden retriever at a dead sprint. The paper describing this result was published in the journal Nature in February 1999, and it landed on the cover. The scientific world didn't just take notice, it was stunned. Physicists who had spent entire careers treating the speed of light as an immovable constant of nature were suddenly looking at a room temperature, or rather ultra-cold, demonstration, proving that speed of light and speed of light in a vacuum were two very different things, and the gap between them could be engineered by human hands to a jaw-dropping degree. But Lene Hau wasn't finished. Slowing light to a crawl was extraordinary. What she did next pushed the boundaries of what most physicists thought was even conceptually possible. 2 years later, in 2001, Hau and her team returned with an even more audacious result. If you can slow a light pulse down to the speed of a bicycle by manipulating the refractive properties of an ultra-cold medium, what happens if you push that manipulation even further? What happens if, instead of letting the transparency window stay open the whole time the light pulse is passing through, you slam it shut in the middle of the pulse's journey? That is essentially what Hau's team did. As the slowed light pulse was moving through the Bose-Einstein condensate, the team abruptly turned off the coupling laser, the beam responsible for keeping that narrow transparency window open. The moment that window closed, the light pulse had nowhere to go. It didn't reflect, it didn't scatter, it didn't get destroyed. Instead, its energy and its information were absorbed directly into the quantum structure of the atoms themselves, effectively imprinting the light's pattern onto the condensate like a photograph developing onto film. The photons, in the traditional sense, ceased to exist as traveling light, but the information they carried didn't vanish. It was preserved, frozen, held inside the atomic medium. Then came the part that turned this from a strange curiosity into one of the most cited experiments in modern quantum optics. After holding this stopped light for a controlled period of time, initially fractions of a second, later extended dramatically in follow-up experiments, Hau's team switched the coupling laser back on. And when they did, the original light pulse reappeared and continued on its way, carrying the same information it had before it was frozen. The light hadn't been destroyed, it had been paused, stored, and then released, fully intact, like hitting play on a video that had been sitting on pause. This is worth letting sink in for a moment, because it's easy to read past it too quickly. Scientists didn't just slow down light. They took a traveling pulse of light, converted its information into a stable quantum imprint inside a cloud of atoms, held that information in storage, and then converted it back into an ordinary functioning beam of light that continued forward exactly as if nothing had happened. It is, in the most literal sense that physics allows, a form of teleportation of information from one physical medium into another and back again. Now this is exactly the point in the story where sensationalized headlines tend to run wild, and where this case file has to draw a hard line between myth and reality. Because getting this next part right is the entire reason this video exists. Did scientists break the speed of light? No, not even slightly. Einstein's speed limit refers specifically to the speed of light in a vacuum, empty space, with no matter to interact with. That number has never been broken, not once. Not in this experiment, not in any legitimate experiment in the history of physics. What Hau's team manipulated was the group velocity of light as it passed through a highly engineered medium, using quantum interference effects that don't exist in ordinary materials like air, water, or glass. Inside that ultra-cold Bose-Einstein condensate, under those extremely specific laboratory conditions, the light pulse's forward progress was throttled down to a crawl by the medium's optical properties, not by breaking a law of physics, but by exploiting one with extraordinary precision. Did they actually stop light in the sense of holding photons perfectly motionless in space? Also not quite, and this is the nuance most viral posts get wrong. What was actually stopped and stored was the quantum information the light pulse carried, encoded into the collective state of the atoms in the condensate. When the coupling laser switched back on, that information was converted back into an outgoing light pulse. So in the strictest technical sense, no individual photon sat frozen in place like a statue. What happened was more precise, more elegant, and arguably more impressive. The informational fingerprint of a beam of light was captured, held in atomic storage, and later reconstituted into moving light again. This is the reality behind the myth, and it's a perfect example of why the popular version of a scientific story and the actual science so often diverge. Not because the real version is less impressive, but because the real version requires patience to understand, and patience doesn't always survive the trip through a viral headline. So why does any of this matter beyond being a strange, quotable fact about a physics experiment from over 2 decades ago? Because this line of research didn't stay confined to a Harvard basement. It opened a door that the entire field of quantum technology has been walking through ever since. Think about what it actually means to store the information carried by light inside a stable physical medium and then retrieve that information intact later on. That is, at its core, a description of quantum memory, one of the essential building blocks needed for quantum computers and quantum communication networks to function at scale. Modern computers store information as electrical charges in transistors. But quantum computers need to store and retrieve quantum information, data encoded not just as ones and zeros, but as delicate quantum states that can be disturbed or destroyed by the slightest interference. Hau's slow light and stop light experiments demonstrated for the first time in a clean and controllable way that light-based quantum information could be captured, stored, and released without destroying it. That's not a footnote in physics history. That's a foundational proof of concept for technologies still being built today. The implications stretch even further. In 2007, years after the original stop-light experiments, Hau's team pushed the concept into even stranger territory, converting light into matter and then converting that matter back into light again, extending the same underlying principle into a demonstration with direct relevance to quantum information transfer between different physical systems. This matters enormously for the future of quantum encryption, a technology built on the idea that information encoded in quantum states can be transmitted with a level of security that classical encryption simply cannot match, because any attempt to intercept or measure that information disturbs it in a detectable way. Slow light and stop light research gave physicists critical tools for figuring out how such systems might actually store and relay quantum information across real-world networks, rather than just theoretical diagrams on a whiteboard. To put this in terms that connect to everyday life rather than abstract laboratory jargon, every time you send a password, a bank transfer, or a private message over the internet today, that information is protected by mathematical encryption. Codes that are secure only because they would take an ordinary computer an impractically long time to crack. Quantum computers, once they mature, threaten to break much of that mathematical protection far faster than classical computers ever could. The proposed solution isn't just building better math, it's building an entirely new physical infrastructure for transmitting information, one where the laws of quantum mechanics themselves guarantee security, because observing or intercepting the information changes it in a way that's immediately detectable. Building that infrastructure requires exactly the kind of capability Hau's experiments first demonstrated. The ability to reliably store fragile quantum information in a physical medium, hold it without destroying it, and retrieve it intact when needed. Research groups around the world, from university labs to companies working on quantum networking hardware, have spent the years since directly building on these foundational techniques, refining how long quantum information can be stored, in what materials, and under what conditions, inching closer, year by year, toward a functioning quantum internet. There's also a deeper, more philosophical layer buried inside this story, one that rarely makes it into the headlines but deserves real attention. For most of human history, light has been treated as something almost mythically untouchable. It moves at a fixed cosmic speed. It arrives from distant stars carrying information about events that happened millions of years in the past. It defines the very structure of causality, the reason effects can't happen before their causes, the reason the universe has a consistent, orderly timeline at all. Watching a team of scientists take that untouchable phenomenon and, within the tightly controlled conditions of a laboratory, slow it, freeze it, store it, and release it again, is a genuine demonstration of how far human ingenuity can push the boundaries of what nature initially seems to forbid, without ever actually breaking the rules nature has set. It's worth pausing here to acknowledge the human side of this story too, because it's easy to talk about lasers and atoms and refractive indices and lose sight of the fact that real people spend years of their lives chasing this result, often without any guarantee it would work at all. Building the equipment alone took years. Cooling sodium atoms down to less than 0.001 of a degree above absolute zero required an extraordinary combination of precision engineering, laser physics, and sheer persistence through repeated failed attempts. Long before the nature cover story, before the media attention, before "the scientist who stopped light" became a line in textbooks, there were countless hours in a lab troubleshooting equipment that didn't behave the way the theory predicted, recalibrating lasers by fractions of a degree, and living with the very real possibility that the whole approach might simply not work. Scientific breakthroughs are so often remembered as single dramatic moments, the day light stopped, when in reality they are the visible tip of years of quiet, unglamorous, occasionally frustrating work that almost never makes it into the retelling. There's also a quieter, less discussed side to this story worth sitting with. Hau built her research group at a time when women in experimental physics, particularly in high-profile quantum optics labs, were still a distinct minority. And she has spoken in later interviews about the added pressure of proving that a result this strange, coming from her lab specifically, would hold up to the fiercest possible scrutiny. When the 1999 paper landed on the cover of Nature, it wasn't just a validation of the physics. It was a validation of years spent building credibility in a field that did not always extend the benefit of the doubt easily. That context doesn't change the physics, but it adds a layer of human weight to a story that's too often told as if it happened in a vacuum, no pun intended, rather than through the sustained effort of a real research team navigating real institutional and professional pressures alongside the scientific ones. That persistence paid off in a way that continues to ripple outward today. Slow light and stop light research directly informed decades of subsequent work in quantum optics, quantum networking, and the ongoing global race to build practical, scalable quantum computers. Labs around the world, from academic institutions to major technology companies, have built on the foundational principles Hau's team demonstrated, refining and extending the techniques into new systems capable of storing quantum information for longer periods across different physical platforms, and eventually, the long-term goal, across real-world distances suitable for a functioning quantum internet. The specific numbers have changed. The core principle Hau proved in that Harvard lab has not. So where does that leave the original claim this investigation set out to examine? Scientists stopped light completely. Is it true? In the most meaningful, scientifically rigorous sense, yes, with the precise understanding of what stopped actually means in this context. Light's forward-moving energy and information were captured, converted into a stable quantum imprint inside an ultra-cold atomic medium, held there under controlled conditions, and later released as an intact, continuing light pulse. That is an experimentally verified, peer-reviewed, published and repeatedly confirmed result. Not a myth, not an exaggeration, and not a violation of Einstein's speed limit. What makes this story worth telling isn't just the sheer strangeness of the achievement. It's what the achievement reveals about the relationship between what nature appears to forbid and what nature actually allows once you understand its rules precisely enough to work within them rather than against them. The speed of light in a vacuum remains exactly what Einstein said it was, an absolute, unbreakable constant. But the space between that vacuum and the real, messy, atom-filled universe we actually live in turned out to be far stranger and far more malleable than most people ever imagined. Somewhere between those two ideas, the unbreakable and the malleable, is where this entire story lives. And it's a reminder of something that applies well beyond physics. The rules of a system and the limits of what's possible within that system are not always the same thing. And the gap between them is often exactly where the most remarkable discoveries are waiting to be found. It's a pattern that shows up again and again throughout the history of science once you know to look for it. Powered flight seemed to violate common intuition about weight and gravity, until engineers understood lift precisely enough to work with it rather than against it. Submarines seemed to defy the basic fact that metal doesn't float, until buoyancy was understood well enough to engineer around it. In every one of these cases, the achievement wasn't a violation of natural law. It was proof that natural law, properly understood, contains far more room for maneuver than casual intuition assumes. Lene Hau's stoplight experiment belongs in that same lineage. Not a crack in the foundation of physics, but a demonstration of just how much can be built on top of that foundation once you understand it deeply enough. And this is precisely the kind of story this channel exists to investigate. Not the version that spreads fastest, but the version that holds up completely once every claim has been traced back to its source, tested against the actual published research, and stripped of the exaggeration that so often gets added along the way to make a headline more shareable. The real story in this case didn't need the exaggeration. Slowing light to the speed of a bicycle and then capturing its information inside a cloud of atoms colder than anything else in the observable universe before releasing it again unchanged was already extraordinary enough on its own merits. It didn't need embellishment. It needed exactly what this investigation gave it: a careful, evidence-based accounting of what actually happened and why it still matters. If this kind of case, a claim that sounds like science fiction, broken down piece by piece until only the verified truth remains, is the kind of investigation you find valuable, there are more of these stories waiting to be unpacked. The next file is already open.